Hello everyone. In this video, I want to show you how to perform an inverse kinematics on a manipulator here. And by the way, this example already exists. I just added a bunch of comments to the script and I'm trying to explain it. So I did not make this script myself, just added a lot of comments to it. So here we have this manipulator and there is the dummy here, which is called target. And you can grab this basically translation or rotation and move it wherever you want at any orientation that you want. And this one here is the point at the end of the gripper. So the goal is to move the joints such that this green point basically comes right to this dummy. Now, when I perform the task, the green point is not going to move. It is going to stay in the same place, but the rest of the robot is going to move and the tip of the end effector is going to come right here and orient it and align it with this frame that you see, this green, red, and blue frame. So this one stays to show you initial basically workspace condition. This is the final workspace condition or pose. And this is your initial joint angles. And then you're going to see the final as soon as I run it. So let's go ahead and run. There we go. You see now the joints have moved and you see that the end effector has the same orientation as the target one and the same location. And again, this green point stays to show you where you started. Another thing that I added to the code that was already existing is it shows the target pose. So you see this location here is basically this X, Y, and Z, and the three angles alpha, beta, gamma are those three angles you see A, B, and G. And then once it reaches that position, it shows you the angles for the joints at the end of the operation. So you see that joint 1 needs to go to 43 degrees, joint 2 needs to go to negative 49 degrees, joint 3 goes to negative 4.9 degrees, all the way to joint 7, which goes to negative 56.3 degrees. So this part I added to the code. And by the way, this robot is a redundant robot. It has 7 links. So when you want to perform inverse kinematics, there is no unique solution. And you can use the pseudo inverse to get basically the minimum norm solution. So let's go ahead and look at the script so I can explain how this task is performed in CoppeliaSim. But let me show you one extra thing. So as I said, you can grab this and move it elsewhere. So let's say now I'm gonna bring it along the Y direction, right? I'm gonna move it, let's say here, and I can rotate it as well, right? So I can grab this and rotate it a little bit, like you can see here, or I can do rotation, let's say about the x-axis, right? So I can rotate it like that, and let me perform the job again. There we go, you see, and it does it very fast. So again, you see that the orientation is the same, the position is the same, and these are the final answers. So now with that you see it is working wherever you move it, as long as you are within the workspace and dexterous workspace, you should get an answer. So let's go look at the script here. So as I said, the script is brief, but I added a lot of comments and I'm going to share it with you on the video description so you exactly understand how it is working. So here you need 2 things to bring in: sim for simulation. You also need sim IK to perform inverse kinematics. You need to bring both of them. And then, and if you want, you can put these in parentheses, something like this, okay? Or you can just have them outside. So then here what we do is we get the handle of the object, we get the tip of the object, that's where the end effector or the tip is, and we get the handle for the dummy target. First thing we do here, we create what we call an inverse kinematic environment, and we use the command create environment under SimIK. Now, what is an environment here? Is it talking about this workspace or so on? That is like a 3D workspace. It's not exactly that. It's more of a memory. It's where the solution is, and basically for each robot you can allocate one of these, because your CoppeliaSim can manage several independent IK at once. So you can have one robot with its environment and workspace in one place, another one somewhere else, another one somewhere else. So for each one of them, you want to allocate one of these environments. Then you here create basically a group. So a group here, which you create using create group under SimIK, and you pass to it the environment and you create a group. The group is basically a solver configuration. So when you solve the problem of inverse kinematics, there are different methods. As I said, the most common one is the least squared method, right? Which is using pseudo inverse, and we call it the undamped method. So here, what I want to do is to create a solver configuration for the pseudo inverse, right? And you see here, I pass to it the environment, I create the group. Now, once I create a solver configuration, I need to set up the parameters for it. So here I say, hey, the environment is this, the group is called the undamped group, and the method I want you to pick is the pseudo inverse, and you have two parameters. 0 here is the damping factor. Now, since it's undamped, you have no damping. And then 10, the next number, is the number of iterations that if you want to solve it numerically, you will use 10 iterations, okay? So this is one solver that you set. Once you have the solver completely figured out, now it is time to give it the target position, the base, the tip, so it can solve. So the next command you use is add element from scene. So you say, hey, with that environment, with this group setting and solver setting, now what you want to do is I give you the base frame as the reference, I give you the tip as where it should move and change, and target as where you want to go. And what you have here is SimIK constraint pose. What does this mean? It means I want you to change the angle such that the pose of the tip becomes exactly the pose of the target. I want the pose of these two to match. And you might say, well, could you do something other than that? The answer is yes. When you do inverse kinematics, you don't have to necessarily, in CoppeliaSim, make sure all the three angles and the three XYZ positions of the tip and target match, or the pose match. You can just have, for instance, just XYZ match. The angles doesn't matter to you. So in that case, you can say something like this. You give it, instead of SimIK constraint pose, you give it this variable, for instance, call it constraint position, which is made by looking at the constraint X or constraint Y or constraint Z. So you say that you have to match basically these positions X, Y, and Z only. Or let's say all you care about is the orientation of it. Then you say, hey, I want you to match alpha, beta, or gamma. Okay, so you only match the orientation. Here you only match the position. If you say this, means you have to match everything. So you can only match specific parts of the pose or the entire pose. Okay, now that everything is defined for the inverse kinematics, the environment, the solver, the setting of the solver, the base, the tip, the or the end effector, the target, the kind of thing to match, Later, now in the solver, you can go ahead and basically use that solver, and the solver here is IK handle group. So this is your solver. You say sim IK handle group. You pass to it the environment, the group. You say it's with respect to the word frame, and then you say get me the result. And then here, this is another thing you have, sim.ik.result success. This means if the solution was successful. Okay, so what this line does is it says if the method of undamped was not successful, this is a not. If the method of undamped was not successful, then run the method called damped inverse kinematics. What is damped inverse kinematics? In my next lecture under playlist robotics, I'm going to explain that, because the pseudo inverse, I bet everybody knows, you have watched my videos under playlist robotics. But what is the damped method? So I'm going to show you that. I'm going to talk a little bit about it, but this is an alternative method. And the good thing about this damped method is this is more kind of successful typically. If this one fails, this one typically doesn't fail as bad, especially when your end effector position or pose is near a singularity. The undamped method or the pseudo inverse can fail. This one not necessarily. The only thing is this one is a little bit faster, more efficient. This one is not as efficient. But again, here is your backup method. So the damp method is a backup method in case undamp is not working. So this one says, hey, run it. If it was not successful, run the other one, okay? And when you run, what would you do now? So let's say you ran this. So what does this do exactly? Does it return the numbers like X, Y, Z of the target or the end effector and the pose and the joint angles? Not exactly. What this one does, it moves the joints such that those two match. Okay, so this one is a motion command. It moves it, it solves the inverse kinematics and make sure they match. So when this matching is done, when the robot moved, now you are getting all of those information to show on the status bar message. Okay, so how do I show this information? Let me show you that. So if we go down here, look. So here you use the command get object position, and you say, hey, get the target position with respect to the base. So get the XYZ of it, and then get the orientation of the target with respect to base. Why do you use target here? Because you assume that the tip has the same position now as the target does and the same orientation, so you can use that. So this is assuming that it has converged. And once you get the XYZ, you can show them, correct? Once you get the orientations, you can convert them to degrees and you can show them. And this is what you're doing here, okay? So you are showing the pose 1, 2, 3 and the orientation 1, 2, 3. So this is showing you the target position. And then you need to get the joint angles, and this is done using the command get joint position. So you go over each and every one of the joints. Look here. So look at what you do. The joints, how would you get the joints first? You get it saying get joints on chain. Sim base, sim tip. So go on the chain that goes from base to tip, get all of the joints. Now from number 1 on the joints to the last one, which is number joints, do what? Get joint position. So this val is going to be the angle of that joint in radians. You convert it to degrees, and then you are going to show it here. You see? So this is the logic of this algorithm, this code here. These extra things that you see I have added is I made sure that when it shows these numbers, it only shows them once. So I added some logic, so when it shows these, it only shows them once when you run the simulation. Otherwise, it keeps printing all of this as long as the simulation is running. It keeps printing all of this message back to back. And that's not what I want. I want one-time display per one-time run. Look here, you see it only showing it one time, and then I stop, and that's it. So the rest of it that you see, there is time and logic for checking. That is for one-time display. Now, I also mentioned that we have a damped method. So this is the other part. I create another solver configuration, this time call it the damp method. And look, the method I use instead of pseudo inverse is called damp list squares. The damping factor is 0.3 and it needs more iterations, 99. And this one is much more stable, but again, at the cost of more iterations. And I do everything again for this, make sure this also gets to match the pose of the end effector with the target. And I have this solution as the backup. Again, this will only run if the first method is failing. If this handle command that I showed you, let's see, here. If the first method fails to bring the end effector to target, then the second method would work. So I'm going to share all of this code with you on the video description. As I said, feel free to play with it. And here I moved the target behind the robot because it was in front of it. I just want to move it behind and show you again that it is working. So let's run it again. You see, it takes a few more iterations, but guess what? Again, I could get it done. And if you want to get closer to singularity, take it closer to the boundaries. Although this is a redundant one, it can have singularities inside the workspace as well. But hopefully with the two backup methods, we should be able to get it to work. So thank you so much for your attention, and I will see you in the next video.